So we're getting into functions that are having more variables, but we of course start with the scalar output. So in particular, we're going to be looking at a function, let's say with three inputs. We plug in into some function rule, and eventually it will return us some scalar. It's going to be a scalar function of three variables. So that's what we're gonna discuss for the entire chapter. And of course, when you think about it, then we want to establish the derivatives. Okay, so that's going to be the partial derivatives, and that's this chapter. And of course, the applications of this topic. Okay. So recall. So what's different? So for Calc 1. It's always a single input and a scalar outputs, like the absolute value function. But then we extend it by doing a vector function, which is a single input, which is the parameter. But then we just give you the curve, where each component is a univariate function in terms of that parameter. And now 15, chapter 15 here, we're gonna do a little bit more general, where we have more than one input. But then, according to some rule, we're gonna calculate a scalar output. For example, we can do something like this, right? So, and you can see that here we have this little f of x, y, z. There are three inputs. Okay, so if there are only two inputs, it's a function of two variables. So in that sense, it's common that we just use z, the third letter, to indicate the output. Okay. And then if you increase the number of inputs, then we'll have to use more letters. So if we use three input variables, then we have to choose another letter for the notation of the output. And it can be more generalized too. So let's say if you have a function of n variables, then what do? So you just have indices for the inputs. So let's just call the output to be cap c, and then we have x1, x2, all the way up to xn. So that will be the general case. So basically, if you think about it, it's just introducing more input variables. So it's like a direct generalization from 2 to 3 all the way up to n. Okay. And let's see examples. So if we have f of x, y, that's defined as a fraction between the radical x plus y plus 1 holding over x minus 1. So here we have a function of two variables, right? And of course, it will return a scalar function, scalar as the output. Okay? So this is a function of two variables. So if we don't really specify the domain of the function, then we just look at all the xy pairs and see what are legal, what are not. Okay. What are the legal inputs? Okay. So its domain is, so let's see. Firstly, we realize that there's a denominator, so the denominator cannot be 0, right? So this tells you x cannot be 1. So And at the same time, we realize that there's a square root, okay? So in the square root, the input cannot be negative. It could be 0, it could be positive number. So that tells you x plus y plus 1 has to be non-negative. Right? So you see there are two conditions, but every pair that satisfies these two conditions will be legal inputs. Okay. And the thing here is that if you want to write it as a set, then you would just need to use the brackets. So basically, it's the xy pairs in R2 such that these two conditions must satisfy, right? So this is the set notation if you want to write it out. And let's see more. So if we have a function of 3 inputs, x, y, z, and let's say we have a natural log of let's say z minus y, and that's plus xy times sine. So now this is a little bit more complicated multivariable function. So basically, when you're calculating the output, you see, okay, we have x times y times the sine of z, and then we plot the natural log of z minus y, right? So the calculation is always not so difficult. So this is the function of 3 variables. And now if we think about the domain, once again, we ask ourselves, so what are the legal inputs, right? So here, sine, the input could be just anything, right? So there's no restriction on z. So the only restriction here is that the natural log, you always input a positive number, right? So you have to have z minus y to be positive, right? So that's the only restriction for our domain. So let's just denote Calc D to be the domain set. So that will be all the tuples in R3 such that, so we just need to make sure that z minus y is positive. Okay. So that's good. So you can see, as long as we know that the inputs are legal, and then, well, the domain is just like a, well, direct extension from univariate calculus, right? Or even tree calculus. But of course, there will possibly, you could think about the range of certain functions. But you also realize that for fraction or for this natural log, so these are the outputs, right? The range will directly relate to the definition of these functions. So let's look at something a little bit more non-trivial. So let's look at the function f of xy. So this is the example that we started with this section, where we have the square root of 9 minus x squared. Theoretical. So its domain is, so now we can directly write down the domain as D, which is the set of all pairs xy in R2. Here, you just need to make sure that the input of the radical is non-negative, right? So that tells you that 9 minus x squared minus y squared is non-negative. So you can see that if you rearrange the variables and the constants, this is actually a disk, right? So this is a disk of radius 3. And now let's think about the range. So not only we know that the input here is negative, but we also know that it has a maximum right? So the input of the radical, this 9 minus x squared minus y squared, this is less than or equal to 9, right? Because we are subtracting squares. So we know that so this tells you what? This tells you the radical here is at least 0, but it's at most 9, right? So if you take the square root, the output is between the square root of 0, which is 0, and the square root of 9, which is 3. Okay. So this helps you to identify the range. Thus, the range of f of xy is the interval from 0 to 3. Okay. So this is the really common interval notation for the parameter, well, let's say z. If we use z to denote the output of the function. So this is so I'm gonna put it in the next one. So this is exactly all the integer, all the real numbers z on the real line between 0 and 3, okay, including the endpoints. Any questions so far? Okay, so you can see, okay, the domain, the range, that's really highly related to univariate functions, right? Now, what about the graphical representations? Graphs and level curves of functions. Of two variables. Okay. So what's a graph? Recall. A graph of a function, let's say y equal to f of x, is the set of all points in the xy plane that satisfies the relationship that the y coordinate has to be f of the input x coordinate. Okay. So basically, we just have a set of all points that satisfies this relationship. So now, if we want to do the extension, then basically we're just introducing a little more variables. So for the graph of the bivariate function, so if we denote z as the output, this is going to be z equals to f of xy. So you see, okay, the function has two variables x and y, but then we need one more variable z to represent this relationship. Okay? And so somehow this is like a three-dimensional plot. Okay? So this is the set of all points x, y, z in R3, and such that the output z always have to equal to the output of the function. So somehow for a bivariate function, we see that if we want to illustrate the graph, it has to be a three-dimensional object. Example. So if we think about f of xy, so I would say that the simplest kind of function is the linear functions, right? So basically we just have linear expressions, 6 minus 3x minus 2y. The graph is what? It's a plane, right? So this is exactly z equals to 6 minus 3x minus 2y. And if you rearrange all the terms to the left-hand side, you will be able to get the node direction, right? Then you will be able to somehow You can also just draw the XYZ intercepts, right? And then you will be able to grab the plane. Okay. Another example. Now let's think about that bivariate function as the radical of 9 minus x squared minus y squared. So still, if we want to do the graph, we have to introduce z to represent the output, and then we still have the option to modify the equation a little bit. So basically, what do we know? We know that of course we can square both sides, and then we will get we can get rid of the radical. And then at the same time, we realize that the z is the square root, which is always a non-negative output, right? So the points on the graph satisfies the following two relationships, right? So this is a combination of the conditions such that z is always non-negative, okay? And at the same time, we can just square both sides. So this is z squared equals to x, 9 minus x squared minus y squared. And this is equivalent of saying x squared plus y squared plus z squared has to be 9. And at the same time, z is non-negative. So it's good. And now we can imagine what this looks like, right? So x squared plus y squared plus z squared is a sphere. It's centered at the origin and has a radius of 3. And at the same time, we have to have the output z to be non-negative, right? So this tells us we are looking at the upper half of the sphere. So if we want to sketch, okay, so this looks kind of ugly. So let's say this is the shape of the sphere. Then graphically speaking, we just have the upper half. So the bottom is the circle with a radius of 3. Actually, I want to make the things dashed underneath x, y axes. So that's a 3. And then we get it up for the z-axis. So this is the graph of our bivariate function here. And this is the upper half of the sphere, right? So this is the hemisphere. That's good. So basically, what does it tell you? So basically, here we know the domain is the disk, correct? So within the xy plane, if you imagine this is going to be lying within this disk, right? But then for whatever input here, you can draw the vertical line all the way up, and it will intersect the surface at some point, right? So so this top point is exactly that point on the graph. Okay? So this is yeah. So let me put it here. So this is the input, in a sense, and that's the output. Right? If we think about the z coordinate, that's the output. So that's the graph. Okay, so in 2D, if we have only one variable, then we have y equals to f of x. That's a curve in the 2-dimensional space. But now here, if we have two inputs, then we have x, y, and we have the coordinate z as the output. So that's going to be a surface. So that's the graph of the bivariate function. Now, level curves. So it's kind of complicated in the sense that if we have a bivariate function, the graph will give you 3 dimensions, right? So what happens if you just want to keep everything in 2D? So that's the motivation of the level curves. So the level curves of f of x, y are curves in the xy plane R2 with equations f of xy equals to z. So basically, we're just looking at all the points xy such that the output level is always k, right? Where k is a constant in the range of our function f. Okay. So basically, this is saying, okay, I'm going to specify, so if I specify an output k, I will draw a curve. If I specify another output k prime, I will get another curve. Example. They are called level curves. Okay. Example. Let's look at this radical again. Okay, so we know the graph is going to be a hemisphere, right? So what happens if we choose different levels as level curves? The level curve with k being, let's say, 2 is the following. So we're just saying, okay, the output has to be 2 for this function. Okay, so that's just not the square root of 9 minus x squared minus y squared has to be 2, and we rearrange the expression by squaring both sides and simplifying. We will get what? We'll get x squared plus y squared is the 5, right? So basically, if you must have an output of 2, so that tells you the radical has to have an input of 4. Okay? X squared plus y squared must be a 5, which is a circle. Okay? A circle in the xy plane. So let's see. Circle. So okay, of course the circle doesn't look perfect, but you get the idea. So here this is x squared plus y squared equals 5, right? And this is level k equal to 2. The output level k equals to 2. Okay, so this k just indicates the output level. And now basically the x-intercept here is the square root of 5. And now, so let's see what happens if we have k equal to 1. So if we have k equal to 1, let's quickly just sketch it. So if k equals 1, then x squared plus y squared has to be 8, right? So it's a little bit larger circle. Okay, square root of 8. Okay. So this is x squared plus y squared equals to 8. And here k is 1. Okay. So now, when k is 2, k is 1, we have the two circles. Now what happens if k is 0? So if k is 0, we will just have the largest possible circle. Let me think. So we're gonna make it black again. So it's gonna be the circle that's actually really close to the red one right here. So the sketching is definitely not perfect, but you get the point. So this is x squared plus y squared, that equals 9. In this situation, the output level is always a 0. And here we have the intercept to be a 3. Okay. So as you can see, we decrease the output level from 2 to 1 to 0. And in this figure, we can see that so the radius changes from square root of 5, which is larger than 2, right, to square root of 8, which is really close to 3, and finally 3. So it looks, the circle looks like it's getting dense. where you decrease the output level, right? So what does it look like in a graph? So it's actually not difficult to sketch. So let me quickly get back to this figure, and let's cheat by copying. So now I don't really need the red part. Right. So so let's think about this. So we have what? We have level 2, level 1, level 0, right? So let's think. So the output we learned that the largest output is a 3, right? So level 3 is actually 1 point right here, right? And then level k equal to 2. The output level k equal to 2 is in black. That's gonna let me just sketch that circle. So the height is 2. So it's somewhere right here, right? So that's k equal to 2. So the purple one is k equal to 3, right? And then the red one is the level k equal to 1. So it's actually cut in between the two black ones. So this one is the red one. I'm going to put very formally so that z is 1 here. X squared plus y squared is 8. And the level is k equals 1, right? And finally, of course, at the bottom, we have the largest black circle, which is saying that we are lying on the circle with center, the origin and the radius of 3, and z here is a 0. So the level is a 0. So you can see that the picture above these level curves is a more condensed representation of your function relationship. Okay? So, so of course, if you want to capture everything, then you would need an infinitely many curves, because the output you can choose infinitely many different values, right? But if you just want to get somehow the train of the function, right? How it looks like. So it's like a graph. Let me think. It's like a map, right? You are just indicating the levels of the elevation, okay, of your hill. But then a graph is just like a three-dimensional illustration of a hill. Okay. Yes. So this is actually, so let me move it to the right. So this is the graph, okay? So this thing is the graph of our bivariate function. And the picture above is just an illustration of like 3 level curves. All right. Let's quickly get into the last topic of this section. So the level surfaces. So now if you think about two variables, we see, okay, either we're going to do level curves in 2D, or we have to increase one dimension and do graphs in 3D, right? So now if we are having 3 variables, that's going to be level surfaces in 3D, okay? So it's just going to get even messier. So level surfaces of functions of 3 variables. So the idea is the same, right? So the level surface of a function f of x, y, z are the surfaces in R3 with equations that the output f of x, y, z has to be fixed as upper level k, where k is a constant in the range of theta f. So as an example, if we think about f of x, y, z, let's say the sum of the components squared. So here the level surfaces are the following. So for whatever constant k as the output, right, we just fix the output of the function as k. Okay. And what do we know? We know that here, since we have a sum of squares, then the range of the function is actually all non-negative numbers, right? So here the level k has to be non-negative. But once you have that, you see, okay, this is actually what? This is actually a sphere, right? This is a sphere with the center at the origin and the radius is spherical, right? So these surfaces are centered at origin with radii spherical. And you can imagine that they are just a sphere stacking all the way up, just extending the radii. So that's one way that you can represent four-dimensional whole relationship between the input x, y, z and the output, let's say, capital.